Let's review our acid properties and see how recovery fits in. Remember that A is for atomicity, the all or nothing property. All the actions in a transaction happen or none of them happen. C is for consistency. If the database starts consistent before a transaction runs, it will end up consistent when the transaction is done. I is for isolation. The execution of one transaction is isolated from that of other transactions, so that the author of a transaction doesn't have to think about concurrency. And D is for durability. If a transaction says it commits, then its effects will persist in the database. The recovery manager is largely in charge of atomicity and durability, but it's also there to roll back transactions that violate consistency. Some motivation for why we need a recovery manager, both for atomicity and for durability. On the right-hand side, you can see a schedule with time going from left to right and 5 transactions T1 through T5. T1 and T3 commit before the system crashes. T2 explicitly aborts before the system crashes. T4 and T5 are still running at the time of crash. So for atomicity, we want to make sure that transactions that explicitly abort, like T2, are able to do so. We also want to make sure that transactions like T4 and T5 that did not commit are abortable during recovery. Now, from a durability perspective, if the database system does crash, which it does in this scenario, we want to make sure that T1 and T3 are durable. Even though T4 and T5 were running at the time of crash, they should not appear as if they ever ran. Okay, so we have both atomicity and durability concerns at the time of crash. The desired state after this system restarts is that T1 and T3 are durable, T2, T4, and T5 should be aborted, and it should be as if they never ran. Okay, before we study mechanisms for recovery, let's just get familiar with the common reasons why transactions abort and the common reasons why database management systems might crash. Why do transactions abort? Well, the most common and most natural reason is because the user or the application explicitly aborts the transaction. Imagine a scenario, for example, where application code has an exception handler. Something in the application logic has failed, unexpected bug perhaps, and we want to make sure that the application undoes anything that it was doing to the database system because it's in a state that we can't understand. All right. So the way that you should handle exceptions in code that reaches out to the database is the code should abort the transaction. But we can also imagine an interactive scenario where a user is working directly with the database and just decides that they don't want to commit their transaction and aborts. And that's fine too. Another reason that transactions abort is failed consistency checks. So this is ensuring the C of ACID, right? So when you get a statement in a transaction that does something to the database that is inconsistent, it violates an integrity constraint, the system will abort that transaction. Imagine, for example, trying to delete a tuple when there's another table that has a foreign key reference to that tuple. One of the possible ways to guarantee consistency in that case is to abort that transaction and not allow you to delete the tuple, otherwise you'd leave a dangling reference. A third reason for transaction abort is deadlock. As we saw, if we do deadlock detection in our system, the way that we resolve a deadlock is we pick one of the transactions on the waits for graph cycle and we abort it. Finally, the case that sort of we think of first, perhaps, is that system failure prior to successful commit, crash in the middle of a transaction, should cause us to abort to guarantee atomicity.